Okay, so let's start talking about the analysis for a simple truss. Now there are two methods I'm going to introduce. Joints method and sections method. Okay, now let's start with joints method. As the name suggests, we'll be looking at joints, okay, by drawing the free body diagram for joints, okay, one joint at a time. Okay. For example, I have this truss right here. Okay. Simple truss, okay, which means that forces are only applied at joints. Okay. And also, this is coplanar, which means that everything is two-dimensional. Okay, it's on this plane only. Okay. So it's just 2D analysis. So I have this truss that's shaped like this that consists of sort of two triangles, and that's symmetrical. Okay, so this AC has the same length as CD. I have this applied load, okay, down the middle, okay, at joint C. Okay, so we're going to call it L. L is a known quantity. Okay, it's a force, right? Okay, first thing I would do is I would draw a free body diagram for the entire truss, for the whole truss. So you draw the truss, okay, label them. Don't draw the attachment, okay. So in this case, this attachment on the left is joint, and this one on the right is a roller, okay. So since I have two-dimensional constraint, so I don't allow this joint A to move in either X or Y direction, so there will be reaction forces at this support, right? So RAX and RAY are the reaction forces. I have this load right here, of course, and I have the reaction force at D. This roller, okay, only constrain the movement, right, in the Y direction going down. So you cannot go any further down. So therefore, the reaction forces going back up. So RD points back up. And that's it. These are all the forces for the entire truss. Okay? Everything else, they don't exist at all. Like the weight of each member, you might ask, what happens to it? Well, in the analysis, okay, of simple truss, we don't usually take into account the mass or the weight of the members. Okay? They're usually ignored because compared to the load applied on the truss, the weight of the members themselves are usually quite small, okay, relatively speaking. Okay, so that's why we usually don't take into account the weight of the members themselves in the analysis of truss, okay, forces in a truss. Okay, so with this drawn, then we can apply the equilibrium equation, right? So this whole thing must be in equilibrium, right? Everything must cancel out. And we do have these three equations in a two-dimensional space, right? Sum of forces equation, right? And these are the X and Y components. The two equations. The third equation, sum of moment. Sum of moment about any point equals 0. So these three equations must be satisfied simultaneously in order for this entire truss to be in equilibrium. And here we have 1, 2, and 3 unknowns. 3 unknowns, 3 equations, no problem. The first equation immediately will give you this result. RAX simply will go away, equals 0. And these 3 equations together will give you these results. Right? RD is simply 1/2 of this load. RAY, the other vertical reaction force, is also 1/2 this load. Okay? So, and that makes perfect sense, right? So whatever load that is, okay, L, let's say 100 Newton, 50 will be shared on this load, and the other 50 will be on this joint right here. Okay? So, in the end, this whole truss is in equilibrium. Okay? Okay. So with this free body diagram for the entire truss, okay, set up and with the reaction forces calculated by applying this equilibrium equation. Now we can get into the joint method. Okay? Here it is. You draw a free body diagram for each joint. Okay? Now, I have this picture set up right here. This is just to help you visualize, okay, the whole analysis procedure. Okay? So I'm going to just draw everything here, right, all in one first. And then I'm going to actually draw the free body diagram, okay, for each joint, okay, individually. Okay, but here, let's look at this whole thing. I basically take the entire truss and take it apart. Take everything apart. Member AB, for example, is right here. Okay, so this label. This is member AB. Member AC, right here. This is AC's member, right? And that's BC, and that's BD, and that's CD member. Okay? So all the members are kind of, I have shaded in green, right? These members right here, okay, these green pieces are there to sort of help you visualize them. Okay? I'm not going to actually use them for the actual analysis of the joints method. Okay? Because I'm actually going to use joints itself, which are here. Okay? So here I have 4 joints, right? A, B, C, and D joints. Okay. So joint A is right here, right? Where these 2 members, AB and AC, meet. Okay? So this is A, but this A belongs to the member. This A is a standalone joint. Okay? So essentially I have taken this joint out. Okay? Taken this joint at the end of this member out. Okay? Take it out of this actual member. Right? Free it up. Okay? Free up in space and just draw the joint. That's all. Same thing for joint B, C, and D. So now these 4 joints will be what I'm going to use for the analysis. Okay? So basically what I've done here is just take everything apart, right? And then just separate members from joints. Okay. So next thing you want to do is draw the forces. This joint is a free body diagram for joint A. Now this, you can look at it as a free body diagram for a member. Okay? And this is a free body diagram for a joint B. Right? So each individual picture here is a free body diagram. Okay, so since we're dealing with free body diagrams, let's go ahead and look at them one by one. Joint A. Look at this right here. Yeah, free body diagram for the whole thing. At this A right here, well, I do know that I have a reaction force, RAY. Okay? And it is exactly 1/2 of load. Okay? So, just draw that. This is my RAY. Okay? Okay. Now this is a reaction force, okay, for joint A. What else? Joint A, other than this reaction force, is also subject to 2 other forces. One force comes from member AB, okay, coming down this way. The other force comes from member AC, okay, along the AC direction, horizontal direction. Okay, so I have 2 other forces. Just look at this. How many members are touching joint A? Okay, so look at this original picture. This joint A is in contact with these 2 members, AB and AC. So there will be 2 forces coming from these 2 members. Okay, on top of this reaction force. Okay, so I'm going to draw two lines. Okay, something like this. Okay, now I only drew the line, a straight line, but I haven't drawn the arrowhead because I don't know just yet whether this force is going down or up. Right? But I'm going to label it first. I'm going to call it FAB. Okay? I need you to follow this convention too. Right? Whenever you draw a force, okay, coming from a member, always call it F under F subscript something, and this something should indicate which member. So this is F, a force coming from member AB. So FAB. This we call FAC. Okay. Next, you want to think about the direction. Okay? The arrowheads for these two forces. So, which one should they be pointing? Well, look at one force at a time. Okay? FAB. Okay. FAB is going at an angle, right? Where FAC is horizontal. Okay? Now, with our coordinate system set up this way, X going to the right and Y going up. In order for this joint A to be in equilibrium, and that's the key, being in equilibrium, okay? And joint A being subject to these three forces only, nothing else, right? You have this reaction force and these two forces, and they are unknown at this point. Okay? These three forces must, in the end, make joint A be in equilibrium, which means that these three forces must cancel out each other in the end. We have this reaction force going up. You do know that, okay, from this free body diagram for the whole bridge, for the whole truss, right? So this goes up, you know. This means that something else must come down to counter this RAY. And the only downward force possible is coming from FAB, because FAB is slanted. And this downward force to counter this guy is the Y component of FAB. Okay? So FAB has a Y component going downward, okay, to counter RAY. Right? So that's the only way that this joint A can be in equilibrium. Okay? Now, since I know the direction of FAB Y, I'm going to call it FAB comma Y, okay, to signify the Y component. And notice that I use dashed lines. Okay? Knowing the Y component direction, immediately you know the X component direction, okay? Because they must follow through. The X component must point to the left. And knowing the component's directions, immediately you know FAB direction, which is, well, you must follow the direction, okay, of the component. So FAB points into the joint this way. So FAB points downward into the joint. Okay? So, similarly, for this FAC, to figure out the direction of FAC, just look at the rest of it. Something must counter FAC, right, horizontally. So, look at this dashed line right here. Okay? This is the X component of FAB. It points to the left. Therefore, FAC must point to the right to counter this guy. Okay? This is actually FACX. Okay, but kind of cramped right there. So, okay, so now the picture is complete. So I can actually draw this joint A separately. Okay, let's do that.